Good morning to one and all. Myself, Dhanasekhar S., Assistant Professor, Department of CSE, Shriram Engineering College. Today we discuss about the following topics. The first one, planar graph. Second one, Euler formula for planar graph, non-planar graph, and then theorem. So what is a planar graph? First, let us understand what is a planar graph. A planar graph is a graph that can be drawn on a flat surface without any edges crossing each other. The edge should meet only at vertex, not anywhere else. Sometimes a graph looks like edges are crossing, but if we redraw or reconstruct it properly, the crossing may be disappear. Example, consider this graph. This graph is a normal graph that is called pi-party k 2,3 graph. That is means here 2 vertex is a one set, another 3 vertex is another one vertex. This graph is converted into or reconstructed into a planar graph like this. So this graph is also called, this graph also contains 5 vertices and equal number of edges and equal number of vertices in normal graph. Consider the following 3 examples. The first graph is a planar graph, but here the many edges are crossed each other, but this graph is a planar graph. The second one graph is also called planar graph. There is no edges are crossing each other. All the edges are properly constructed. And third one graph is called non-planar graph. Here maximum number of edges are crossing each other. So consider the first example. To reconstruct or redraw into planar graph. So draw the circle. There is no intersect each other. So and then draw this edges and next one and next one and last and last. So here 2 vertex, first one. So this is way to reconstruct this graph into this one. This graph is called planar graph. The edges meet only at vertex side. No edges cross each other. The same graph may look crossed at first, but we can reconstruct or redraw without crossing. How to check if graph is a planar graph? There are 2 main important conditions. We will check the graph. A graph is a planar if and only if it can be redrawn without edges or crossing. This is the first condition. Second condition, the graph does not contain the non-planar graph as a subgraph. The following graph. First one, complete graph K5, and second one, complete pi-party graph K3,3. These rules comes from important scientist theorem. How to identify the faces in planar graph? When a graph is drawn in planar way, it creates a regions called faces. A faces or regions is an area surrounded by edges. There are 2 types of faces. The first one, internal faces, region inside the graph. External faces, second one, that is called outside infinity region. The next formula, Euler formula for planar graph. This is a very important formula. The given planar graph is exactly planar graph. The following condition to be satisfied. This graph give a fundamental relationship between vertices, edges and faces of connected planar graph. The formula is V minus E plus F equal to 2. The V is called vertices, number of vertices minus number of edges plus the number of faces or regions equal to 2. For any connected planar graph, when the graph is drawn a planar way without edges or crossing, the number of vertices, edges and faces will always satisfy these conditions. This formula derived by Euler. So consider the previous example, same previous example. This is a normal graph, non-planar graph. This graph is reconstructed into planar graph. This is converted into planar graph. From this planar graph, we calculate the number of vertices. Total we have 5 vertices and 6 edges. 1, 2, 3, 4, 5, 6 edges, and faces are 3 faces. So one faces, that one phase 1 is surrounded by these edges, surrounded by or enclosed by edges, and phase 2 or region 2 is surrounded by these edges, the following edges, and third edges is external edges, external faces outside of the graph. So we have 3 faces, 2 for inner faces and 1 for outer regions. So we apply this parameter into our Euler formula, V minus F plus V minus E plus F equal to 2. So 5 vertices minus 6 edges plus 3 faces equal to 2. So answer is 2 equal to 2. So hence the formula is satisfying. So another one example, we calculate the number of faces in given graph. They give number of vertices and number of edges to find how many number of faces or regions. So we apply this value into our Euler formula. So we have 6 vertices and 9 edges. We don't know the faces. So plus F equal to 2. So F equal to 5. So we have a total 5 number of faces. So the important conditions for planar graph, if you use a Euler formula, first the graph must be a planar, second one the graph must be connected. And next, understanding the phases in graph. So already we discussed about how to calculate how to find the phases in a graph. The normal graph or a non-planar graph is converted into planar graph like this. So after we calculate the phases, as per our definition, the faces are enclosed by edges. So in this planar graph, we have 3 inner faces and 1 outer faces. So total 4 faces or 4 regions, but normal graph we have 5 faces or regions. Next important result derived from Euler formula. If our planar graph to satisfying the following 2 conditions, if our graph have total number of vertices is more than 3 vertices, to satisfying the first condition, that is called E less than or equal to 3 into vertex minus 6. Second one, for biparty planar graph, if our graph is a biparty planar graph means, so to satisfying the second condition, edges is a less than or equal to 2 into number of vertex minus 4. So these are two important formula for our planar graph that is introduced by Euler. And next one, non-planar graph. Some graphs can never be drawn without edge crossing. These graphs are called non-planar graph. There are two important non-planar graphs are the complete graph K5 and second one the complete biparty graph K suffix 3, 3. So K5 means we have a 5 number of vertex. Each vertex is connected to the remaining other 4 vertices. Similarly, K suffix 3, 3 is we have a 2 set of vertices. First set have a 3 number of vertex. Second set have a 3 number of vertex. Each vertex is connected to the remaining other vertex in other set. Remaining vertex in other set. This is a most important non-planar graph. Complete graph with 5 vertex K5. Every vertex connected to every other vertex. So we have a total 10 edges. So cannot be drawn without crossing. So K33. It's a complete biparty graph. K33 is a 2 set of vertex. The set 1 contains A, B, C and set 2 contains D, E, F. Every vertex in set 1 connected to all the vertex in set 2. The total number of edges are 9 vertex. The real life example of non-planar graph is utility problem. 3 house, 3 utilities, water, gas connection, electricity. Each house must connect all 3 utilities without crossing line. It is possible. So K3, 3 is a non-planar graph. Next theorem is important theorem for finite graph is a planar graph if and only if it does not containing the subdivision of or a subgraph of complete graph K5 and complete biparty graph K3, 3. Instead of trying to redraw or reconstruct the graph again and again, just check inside the graph. If you find the structure similar to K5 or K3, 3, the graph is a non-planar graph. And so this is an example for K5 graph. So we apply the formula and Euler formula. We have a two formula in Euler formula. The first formula E means edges less than or equal to 3 into vertex minus 6. We apply this number of vertices 5 and edges less 10. 10 less than or equal to 3 into 5 minus 6. We have 10 less than or equal to 9. This is not satisfying the condition. So as per the Euler formula, the given graph, the graph is complete graph K5 is non-planar graph. The similar way, this is a biparty graph K3, 3. We apply this graph parameter to Euler formula. E less than or equal to 2 into V minus 4. So on the number of edges are 9, number of vertex 6. So after calculation, the 9 less than or equal to 8 is not satisfying the Euler formula, second formula. So this graph is also non-planar graph. And next move to applications of planar graph. Planar graphs are useful in many areas. The first one used in circuit design to avoid wire crossing or circuit crossing each other. Second one used in network layout designing in computer networks. Third one geographical maps. Fourth one topologies. And next we discuss about the properties of planar graph. So we have totally 7 properties. These are very important properties. The first one, Euler formula for planar graph. This property to tell us the relationship between vertices, edges and faces in planar graph. That formula is E minus V plus F equal to 2. And second one, maximum number of edges are edge bound for planar graph. The second property. And this is third one, property for pi-party planar graph. And fourth one, minimum degree property. This property to tell us total number of degree of each vertex is less than or equal to 5. If any one vertex is more than 5, the graph is called non-planar graph. Less than or equal to 5, total number of degree less than or equal to 5, that graph is maybe planar graph. Okay. Fifth one, face degree property. The sum of degree of all the faces equal to 2 into number of edges. And sixth one, non-planar graph condition. Seventh one, region property. So these are 7 important properties of planar graph. Thank you.